If we view mathematics as a game, and we should, the definitions are the rules of the game. You can't play unless you know the rules. But what is a definition? So without going too deep into the philosophy, we can say that a definition claims that two concepts are the same thing. For example, we have this concept of a square number, and we have this concept of a product of an integer with itself. And our definition says these two concepts are the same thing. And this means that if you have a square number, then you have the product of an integer with itself. And also, if you have the product of an integer with itself, then you have a square number. And in general, this means that every definition corresponds to a conditional and its converse, both of which you accept as true in order to play the game. So, for example, let's rewrite as two conditionals. The root of a polynomial is a value for which f of a is equal to 0. So remember, a conditional can be viewed as if you have something, then you have something else. So here we have a root, and our definition tells us that f of a is equal to 0. And since it's a definition, the converse is included. So rewriting as two conditionals, if x equals a is a root of f of x, then f of a is 0, and conversely. We could write this as a biconditional. However, it's useful to keep the conditionals separated. Sometimes we want to prove that something isn't. A number isn't rational. A function isn't continuous. A limit doesn't exist. How can we do this? Remember, to define something A, we accept two conditionals. If A, then B, and if B, then A. But remember, a conditional and its contrapositive are equivalent. Since we've accepted these conditionals, we should also accept their contrapositives, which will be. So if we want to show that something isn't A, we'll use the contrapositive that concludes not A. So for example, a number is a square-free integer if it lacks a repeated prime factor. Let's rewrite this definition as two conditionals, then determine what would be necessary to prove a number is not square-free. So as two conditionals, if a number is square-free, then it lacks a repeated prime factor, and the converse, if a number lacks a repeated prime factor, then it is square-free. So let's also write down the equivalent contrapositives. So we want to negate the antecedent and consequent and switch them. So this first one lacks a repeated prime factor. The negation must be that it has a repeated prime factor, and is square-free becomes it's not square-free. And for our second conditional, is square-free becomes not square-free, lacks a repeated prime factor becomes has a repeated prime factor. So remember, the last thing you write is what you proved. So if we want to prove that a number is not square-free, that needs to be the end. And in order to get there, we'll need to show that the number has a repeated prime factor, and we start somewhere. As the statements get more complicated, it may help to write them out symbolically, then find the contrapositive and other logically equivalent statements. For example, a glurby is defined to be a quasit that is not a fleuron. How could you show that something is not a glurby? So rewriting our contrapositive will be a little easier symbolically. So let G be something that's glurby, Q be something that is quasit, and F be something that is a fleuron. So our definition, if something is a glurby, then it is a quasit that is not a fleuron. We can write that as, and the converse, if something is a quasit that is not a fleuron, then it is a glurby. We can write that as, to prove something that is not a glurby, we'll use the contrapositive. and it'll be the contrapositive of the first statement, because there our antecedent is a glurby becomes a consequent not a glurby. We can use De Morgan's laws to rewrite the negated antecedent, which will become and we do need to be a little bit careful when we write this. It's correct to say that this is not quasit or a fleuron. But remember, when we say not A or B, this suggests the negation of the union of A and B. And that's not what we want. So we should try to avoid the construction not A or B. And so we could write it as if something is not a quasit, comma, or a fleuron, then it is not a glurby. An even better construction makes it clear that we're talking about two different things. If something is not a quasit, or it is a fleuron, then it is not a glurby.